Okay, let's start. Welcome back to the tutorial of GANs. Next speaker is Professor Sanjeev Arora from Princeton University. So he has too many awards to name within 1 minute. So I think he was awarded the Goodfellow Prize twice, and the highest theoretical computer science award. So just let's welcome Sanjeev Arora. He will talk about the foundations, theoretical foundation and limitations of GANs. Welcome. Also, it's a 45-minute talk. So.
Glad to be here. Thanks for inviting. I did put theory in the title just to alert you that it's a somewhat different talk than we are used to at this conference, but there's not a lot of theory in the talk per se. So it's based on these two papers with from ICML and ICLR with this group of co-authors, Rosca, Jun-Yan, Taesung, Andrei Ristesky, and Jun-Yan. For purposes of this talk, GANs are distribution learners. So they're trying to learn distribution. This is in line with the canonical framework introduced in the original paper of Goodfellow and the many follow-up works. And I realized that in many vision applications, including some of the talks today, GANs are used for image-to-image mappings, to learn image-to-image mappings. There's not much theory of that I'm aware of, and most of the theory that exists has been in the context of distribution. So that's the setup that I'll be talking about. And the main question about that I see there is to how to even quantify the success of training for such an implicit model. So you can see the nice pictures at the end, and you can try to look at the pictures for artifacts or whatever, but is there a way to quantify it? So this, of course, doesn't arise for classical deep learning, where you're trying to classify, where it's completely clear what's generalization. But in these distribution learning, it's not completely clear. And the dominant mode of analysis that you may have seen, and also in Ian's talk this morning, it assumes very large deep nets, infinitely large training time, number of training samples, etc. So there's this asymptotic theory. And the main message of the rest of the talk is that there's signs of trouble in this asymptotic theory, that it inherently does not seem to apply to the finite case, where you have a deep net discriminator with 1 million or 5 million parameters. 5 million is less than infinity, and there's signs of trouble. Okay, so just to situate you in the kinds of questions that we are trying to understand here. So here are some things we'd like to understand about GANs. We'd like to have theory. So what distributions can be generated, possibly approximately, by your favorite CONNET architecture of size n? So if the generator is some CONNET architecture of some size n, with a norm bound, let's say, what distributions can it even generate? It's not completely clear that 5 million parameters suffices to generate images of the real world that we all want to generate. Does an equilibrium exist for the training game? Under what conditions, including how much training time, samples, what objective, etc. This training conversion and equilibrium. Then next, assuming the equilibrium is reached, what guarantees do we have about the generator's distribution? Is it close to the training distribution? So obviously, if the distribution we're interested in cannot even be generated approximately by the CONNET architecture that we've chosen, then obviously the answer here would be no. There's no guarantees. But assuming your CONNET architecture is capable of representing the distribution, then you could ask this question. And Goodfellow in this foundation paper showed that all's well when net's training samples, training times are large enough. Because if the net is large enough, clearly it can represent any distribution. That's clear because even a mixture of Gaussians, when you make it very large, can represent any distribution. So the first point is trivial, and the second point and third point is also not too hard because the nets are really large and they can basically represent anything, any discriminator, any generator, etc. So, and in this talk, as I already alluded to, we see that if the discriminator is finite and modest size, this message is incorrect, regardless of the training time, number of samples, training objectives. Okay, so there's this big gap in GANs theory, and currently I don't see a way to fix that, although I'll talk about at the end directions in which you could fix this. So now the first part of the talk is for the consideration of these questions of equilibrium and generalization for finite size nets. And this is from this paper with Rosca, Jun-Yan, and Yijian. So as I alluded to earlier, for these for generative models, it's not completely clear always what is a good notion of generalization. How can we decide that this particular model has learned a distribution? And the difficulty, of course, is that the distribution has very large, is supported on a very large number of images, very likely infinitely many images. So how do you test it? And so these generative models, the classical ones, things like denoising autoencoders, variational autoencoders, etc., are mapping, say, white noise or some other canonical distribution of seeds into some realistic images. So they're mapping, say, the Gaussian distribution to some very complicated real-life distribution, D sub real. And in these classic models, you have a training objective which is very different from GANs, which is to maximize the log likelihood given to the data. And then the generalization notion is easy to define, namely that this notion has to be similar for training and test data. Okay, and so then if you can check this log likelihood under held out data or test data, and that gives you some confidence that at least the training made some kind of sense. Okay, it doesn't show that you actually learned the distribution, but it's certainly showing you that you tend to assign some reasonable probability to images that you actually sample from the real distribution. Okay, so it's not that the distributions are the same, but at least you're assigning good probability to the images. But GANs, as you know, come with no estimate of log likelihood. So it's different and different from these earlier models, and this is both its strength and its weakness. So the strength is that because you don't try for because in the old models, because of this log likelihood objective, what they do is they tend to smear out the probability. They tend to smear out the distribution. So they are sort of putting noise in the output so that it gives non-zero probability to basically any image. So GANs don't have to do that, so they can produce sharp and clean images, which we all love. But then they come with no estimate of log likelihood, so this classical notion of generalization cannot be applied. So instead, what they do, as you all know, this is just a quick reminder slide, is that there's a discriminator, which is a neural net, and it's going to try to distinguish between the two distributions, the real distribution and the synthetic distribution. And we consider the synthetic distribution to be good if this finite side discriminator, regardless of how hard it tries, cannot distinguish between the distributions. So in other words, yeah, there's a two-person game really, where the discriminator is being trained to output 0 on real inputs, and 1 on real inputs and 0 on synthetic inputs. In other words, high values on real inputs and low values on synthetic inputs. And the generator is trained to produce synthetic inputs that make the discriminator output high values. And this objective that the discriminator is doing that and the generator is doing that is phrased as this minimax objective, and that's exactly saying that that the discriminator is trying to give high values to the real distribution and low values to the synthetic distribution. And the reason for the log in the original paper is that it is a nice information theoretic objective, but now, of course, there are many other objectives, and just as illustration, here's a more intuitive objective, the Wasserstein GAN of Arjosky et al., where you replace the logs by just the probability of outputting one. So now you really have just the difference of two probabilities, namely the probabilities of the expected value of the output on the real distribution and the expected value of the output on the synthetic distribution. And one player is trying to minimize that difference, and the other is trying to maximize. The discriminator is trying to maximize, the generator is trying to minimize. Now, this is just for illustration, the Wasserstein GAN. The results I'm going to talk about, the limitations of GANs, applies to basically any standard objective, any of these divergence objectives. Okay, and an equilibrium is when one player wins, and of course the equilibrium we are hoping for is that the generator wins. The generator at the end is producing such a great distribution that further training of discriminator doesn't help. Okay, so namely this maximization of all discriminators from this architecture doesn't help. Okay, none of them can distinguish the two distributions very much. So let's call that an equilibrium. That's a desired equilibrium. There could be other equilibria in this game, but that's the desired. So there's some good news and bad news. So we show that there is always such an equilibrium. So a winning equilibrium with a fairly modest sized generator and discriminator. But there's bad news. Let me tell you the bad news. So which is linked to this good news. So if discriminator size is n, so this is a sort of toy version of the result because I'm quantifying the size of the discriminator generator by number of parameters. Now, of course, in deep learning, we know that number of parameters is not always an accurate reflection of the capacity of the deep net. So you can replace it with some suitable norm estimate of the size or whatever. But just as a toy statement of the result, I'm using number of parameters. So if the discriminator size is n, then there exists a generator, and the generator is also a modest size deep net, that generates a distribution supported on n log n images, and still wins against all possible discriminators from this class. And this is true for any standard training objectives, Shannon, Wasserstein, etc. This is surprising because the set of possible images, the real-life distribution, presumably has infinite support. Right? Real-life images, there's infinite many pose, combinations, sliding, all kinds of variables, and so it's effectively infinite. Certainly trillions, but n maybe like a few million, right? The discriminator size. So this is saying that the support size in this equilibrium is not so large, okay, of the order of millions. Okay, so there exists always bad equilibrium with finite size discriminators. The rest can all be infinite. You could have infinite number of training samples, you could have infinite training time, whatever. It doesn't matter. So the message here is that small discriminators, the theory of GANs for finite size discriminators, is inherently very different. Okay, small discriminators are inherently incapable of detecting molecules. And this is a different kind of failure mode of GANs training that people were always worried about. The failure mode people always worry about, a lot of people worry about, is that the generator has somehow memorized the training. This is not that failure mode. The failure mode here is that it has learned some images, they could be new and original, but there isn't a lot of them. Okay, so many of the existing empirical things that people do, like checking that the images are not close to the training images, these could be all original images, but so they don't look like the training images, but the total support size is small. So that's a theory. That's a theorem. So let me explain why this holds. Okay, what's the difference between the infinite theory and the finite theory? And this has to do with the counterintuitive nature of high-dimensional geometry. And maybe this is not always appreciated by people who haven't thought about high-dimensional geometry. So here's a very startling fact. I remember learning this in grad school, and at the time it was very, very counterintuitive. So in d dimensions, so think of d as large, even a few hundred or a few thousand. So in this case, dimension is going to be like the number of parameters, okay, so which is rather large. So, but even for 1,000 or a few thousand, it's this whole. So they are exponential in d directions, whose pairwise angle is at least 60 degrees. Okay, so as opposed to the two dimensions, right? There are only 6 directions whose pairwise angle is at least 60 degrees, right? But in d dimensions, they are exponential in these many directions, with pairwise angle of 60 degrees. So I draw it as this kind of sea urchin kind of figure, that in a 3-dimensional sea urchin, because you have a lot of spines, the spines have to be all packed together very closely. But in d dimensions, you could have this urchin where all the spines make an angle of 60 degrees with each other, and they're still exponentially many spines. Okay, and a related fact is that, yes, they are exponential in d directions, but there's not a lot more. So they are exponential in d over epsilon, for any epsilon, special directions such that every other direction makes an angle of at most epsilon with one of these special directions. So the so-called epsilon length. Now these are massive numbers, massive numbers, okay, exponential in d over epsilon. But the point is that in the theorem, all of these exponential numbers will become the logs, okay, and that's where the bad news comes from. So now let me tell you why low support distributions can fool the smallest way. And this is just a taste of the arguments that are used in the rest of the results as well in this world. So here's the first idea. So deep nets are Lipschitz with respect to trainable parameters. This is a very intuitive notion. Lipschitz just means that if I tweak a parameter a little bit, it shouldn't have a lot of effect on the output. So they are Lipschitz in that sense. And there's some Lipschitz constant. And this Lipschitz constant actually plays a role in the theory, and it's not very large for real life. And it actually enters into the theory only as a log of the Lipschitz constant, so it's really mild. Now the second idea is if the number of parameters in the discriminator net is n. And remember, this is again my toy analysis for this talk, where I'm equating the capacity of the deep net as the number of parameters. So if the number of parameters is n, then they are only exponential in n over epsilon, fundamentally distinct deep nets. Okay, so now I'm thinking of a deep net as a vector in n dimensions, right? It's n parameters, it's a vector in n dimensions. And from the previous slide, in n dimensions, there are these special directions, exponential in n over epsilon, distinct directions, and those are the fundamentally distinct deep nets. All the others make a low angle with these, or low inner products with one of these canonical deep nets, and so everybody else is supposed to know these. And now the synthetic distribution can just be a random sample of n log n over epsilon squared images from the real distribution. Okay, so the discriminator has somehow memorized or learned to produce n log n over epsilon squared realistic images. And now, because it's a random sample, for every fixed discriminator, the probability that this random sample discriminates between the two distributions, real and synthetic, is very small. Okay, this is a standard concentration bound, Chernoff bound, goes by many names. But this probability is very, very small, exponential in minus n over epsilon. So even with n log n over epsilon squared samples, you can get these ridiculously low error probabilities. And so now we're using idea 2 that there are only that many fundamentally distinct deep nets, and this very tiny probability, you do a union bound, that the union of the probability of the union of events is at most sum of the probabilities, you get that none of the discriminators can epsilon discriminate between the synthetic distribution, the simple synthetic distribution, and the real distribution. Okay, if you're seeing epsilon nets and this kind of high-dimensional geometry arguments for the first time, maybe you didn't quite fully absorb the argument, but it's just the simplified, the way vectors are tracked. Okay. So yeah, so this is the problem, that with n parameters, you really, n parameters are not capable of distinguishing between distributions that support n log n or epsilon squared and infinite. Okay, so we had these results, and I talked about these at a workshop a year ago, and Jan was there, and Jan and he said, "Yeah, interesting." So probably most people have seen Jan has been a very big supporter of GANs and thinks it's a great idea, and maybe the best idea in machine learning in many years. So he saw this and he said, "Yeah, interesting. Yeah, so the original GANs idea seems to have some problems, but there's this new idea, the encoder-decoder GANs, which gets around the issues that we showed, the more collapsation. So there are these papers by GANs, adversarial low networks, and then since then many others. And I saw that, then he told me about the encoder-decoder GANs, and I saw it, and I saw, okay, yeah, this really breaks up proof. I don't know if it gets around the issues, but it certainly completely wipes out a proof. So I said, oh, maybe encoder-decoder GANs is the way. So then we thought about it for a few months, but part 2 of the talk is that encoder-decoder GANs also do not get around these issues. And this is actually a very interesting construction. And it requires one clever insight. Okay, so let me tell you the encoder-decoder intuition as I see it. I see it as just formalizing the old manifold intuition that people have always had in computer vision. That even though that in the pixel space, images are these very complicated vectors, but that there is a mapping, a simple mapping to some underlying manifold which is much lower dimensional, and so every image maps to some code on the manifold. So in the encoder-decoder GANs, you have not just a generator. So the generator would be mapping points on the manifold to the image. So that's the standard generator, mapping manifold to the image. But with the encoder, you also want the reverse map, the image to the code. So now the discriminator wants to see not just generated images, but also their code. So in some sense, he's peeking at the things that were hidden before, right? He's looking at the code that the image came from. Okay, and so that's the first discriminator, and he's expecting to see an image and its code. And the generator player, what was a generator player, is now a player which has 2 deep nets, namely a generator and an encoder. And this is player 2. And, whoops, sorry, this is one of those mix-ups with the fonts that happened with earlier slides too. So, so this is still the setup, which, fonts are there. And the discriminator is now distinguishing between 2 settings. One is when it's given a real image and its code, okay, according to this encoder. So that's one setting. And the second setting is where it's given the output of the generator using a random seed and a random seed. Okay, so it's sort of allowed to peek into the guts of the generation process. Right? It's allowed to look at the code. And that really seemed originally, when I first looked at it, seemed to completely break the previous proof, because there it involved a generator who sort of memorizes a small set of images and learns to generate them. And then for that kind of generator, if you start looking at the code that it's using, it sort of inherently will. It seems like the 2 distributions are very different, and the discriminator should be able to discriminate them. in general, yeah, in these encoder-decoder setups, you imagine that this code has some semantic meaning, right? And people have been using encoder-decoder GANs for that purpose, that the encoder somehow captures some semantics. All right, so now the player one is trying to maximize discrimination probability between these two settings, and player two is just like that. All right, so here's the theorem from the ICLR paper. There now exists an approximate equilibrium. Approximate just means that the loss isn't zero, but it's epsilon, some very small amount, which is basically all you hope for anyway in real life training. You don't ever get loss to zero. You just try to get it to some small constant. So now the theorem is that there exists an approximate equilibrium such that player one is fooled, the discriminator is fooled, but the generator produces a distribution of low support, and furthermore its encoder, which you hoped that was going to produce some meaningful codes, actually maps an image to completely uncorrelated white noise. Uncorrelated white noise. So in the construction, the code it produces given an image is completely uncorrelated white noise. So it's the worst imaginable failure mode possible. Okay, this is just showing the existence of an equilibrium. Whether or not this happens with your favorite training and your favorite regularizer, etc., the theorem does not say. Just that it exists. The bad solution exists. So basically, the takeaway message in these results is that there's no magic in the training objective. Somehow if you tweak the training objective and hope that it inherently fixes the issues, that's not going to happen. Alright, so here's the proof idea. And this was a key aha moment. So we're going to assume that the images have been corrupted with white noise in a fixed pattern. So some pattern that you can extract. Now, for the purpose of this talk, just assume that, say, every 50th pixel is random. Okay, just for illustration. In general, you could just assume that there is some source of stochasticity in the image, and you can extract some random seed out of that stochasticity. Okay, that's the assumption. But for this talk, you just assume that every image has been corrupted this way, so that every 50th pixel is random. Clearly, these still look like realistic images, and that's the real distribution. Okay, that the GAN is trying to do. So now the encoder is going to map this image, the noised image, x plus eta, to its noise pattern. That's the encoder. Okay, so this is some small net, right? It's extracting out every 50th pixel. So this is a very trivial encoder. Okay, it's clear, we can see that it's not doing anything meaningful. It's not extracting any meaningful features. Nothing. Now the generator is a construction that again uses high-dimensional geometry a little bit. It randomly partitions all Gaussian seeds into a small number of regions, associates each region with a single image. So it's sort of again doing some kind of memorization, but it's doing it in tandem with some partition of the Gaussian seeds. And so there's the picture. It's sort of partitioned this set of all Gaussian seeds into a small number of regions, and now it's for each region it's memorized an image, and given a seed eta, you take the image associated with this region and output x plus eta. So clearly, by construction, this generator is only able to output a finite set of images, distinct images. Okay? But those images come with this random noise and the random code. And it can be shown, again, by those epsilon n kind of arguments, that this finite discriminator cannot distinguish this kind of generator and encoder nets from creators. Okay, so the theorem suggests that GANs training objectives and these encoder-decoder setups are not guaranteed to avoid mode collapse. So the question is, does this happen during real-life training? So I always emphasize that the theorems are just showing existence of that equilibrium. Whether or not it happens with your particular initialization, your particular architecture, your particular regularization, whatever, not guaranteed. Because it just shows the existence of data. The training may not find that. And by the way, this is not an idle speculation, of course, because we all know now that even for classification tasks, deep nets do have bad solutions, right? They are able to even memorize random labels or really bad data. But somehow when you train them on real life data, they avoid those bad solutions. So this is not idle speculation. That real life training may somehow work, right? So that's part 3 of the talk. We show empirically that mode collapse happens. Now this work is actually maybe from last fall. So I realize things move along fast in this field, and we haven't checked all the latest and greatest generators. Okay, so this is things that we knew of last fall, before Isola. Okay, so how do you check mode collapse in a real-life distribution? Now, of course, there are all kinds of tests people do, like they take two generated samples and draw a line along that and show that somehow there are interesting images along that line. Or all kinds of other tests. Turns out that most of those tests that I know of, the existing tests, can still be fooled by a distribution that has mode collapse. There's no guarantee that mode is mode collapse. Okay, all they're showing is that there's some interesting structure to the space, but that isn't avoid mode collapse. So we introduced a new test based on the birthday paradox. Now, maybe you remember this from your undergrad discrete math course. So it's a trick we like to pull on undergrads in this undergrad discrete math. That if you have 23 random people in a room. Now maybe this used to work better when computer science used to be smaller majors. These days, there's no class in the computer science department which has only 23, including random classes. But okay, we used to pull this trick. Once you have 23 people, random people in a room, it's actually quite likely that 2 of them share a house. And that's called a paradox because you would imagine naively that you need 365 people in a room before you're guaranteed or have a high chance of a collision, right? So 2 people have the same birthday. But actually 23 suffices. And the asymptotic version of this birthday paradox is that if a distribution is supported on n images, then the probability that a sample of size n has a duplicate image is at least enough. Okay, this provides a lot of power to us in looking for mode collapse, because we imagine the number of modes is like in the millions, let's say a million. So no human can look at a million images and try to see if they're the same. I mean, certainly I would die with that. But square root n is much more manageable. Square root of a million is 1,000. And then you can start to do things. So this is a birthday paradox test, that if a sample of size n has near duplicate images, sorry again, the font has problems on this computer. It has near duplicate images with probability more than half, then the distribution only has something like s squared distinct images. Okay, there's an asterisk in this, and that's explained in the paper. And the asterisk has to do with the fact that what this doesn't rule out is this test is that there's something like s squared prominent images in the distribution, and then a whole bunch of images to which it gives very small probability. That can never be detected by this test, and probably by no test. Okay, but what it does show is that this test suggests is that this distribution is largely supported on s squared distinct images. Alright, so on with this test, there's the birthday paradox test. So now, here's what you do. So this is on Celete faces. And the idea is the following, that you take a random sample, so we hypothesize that because the training set is about 200,000 images, so we said, okay, maybe the support size is about similar as the training set size. And so we said, okay, let's try 500 samples, which is the square root of 250,000. So now we have a random sample of 500 images. That's still a lot for a graph student to look at, right? Like a dozen times or dozens of times. So first you run these images through some heuristic for similarity. So among these 500, you flag down, say, the 25 pairs, which this automated filter thinks are very similar. And now, among those 25, you check visually. The grad student checks visually. So now, of course, there's some issue of judgment. You know, what images are really similar, because of course they're not similar, completely 100% similar at the pixel level, right? But they are sort of similar for any reasonable human being. So now we start seeing these doppelgangers, maybe twins, right? So they're not exactly the same person, but very, very close. So these are some duplicates we found among 500 samples for Radford et al. And then for BiGANs, Donahue and Dolan et al., we get about 1 million duplicates in about 1 million images. Sorry, duplicates among thousands, a sample size 1,000. So the implied support size is sorry. Now, so this means, this suggests that actually this mode collapse does happen. By the way, we checked that we didn't find that these repeated images, it's exactly the kind of failure mode that was suggested by the theorem, and that was not anticipated by previous empirical work. So these repeated images are not images in the training sample, as far as we can tell. So the generator has learned to generate a new image, but it hasn't learned to generate a lot of different images. So just 250,000 or maybe. Another thing that we find is that, remember that the theorem said that the support size is something like n log n, if n is the discriminator size. So we try to vary the discriminator capacity, at least in some naive way that we could see. And indeed, the support size seems to grow near linearly with discriminator size, at least in our limited experiments. So this again is consistent with theory. So in other words, this theorem seemed rather unlikely at first sight, that the generator wins by just memorizing some finite set of images, but actually that is indeed the failure mode we seem to be discovering. Now, if this needs more complete testing, I'm hoping somebody else does it. It does require many hours of grad student time, so that's the bottleneck. I mean, even with the birthday parallels and an automated filter, the grad student still has to submit. We did similar testing on CFAR. By the way, as I said, this was last fall, so we didn't have the ImageNet work that has been done since then. So this was on CFAR. We took the state-of-the-art models then, and the StackGAN. And again, we find, we look for duplicates within image categories, and you remember image categories have 10,000 images. And so we find duplication collisions for the subcategory with 100 samples, so that implies about 10,000 images. Horse 200 samples, so that's 40,000. 40,000. And dog is 300 images. Oh, sorry, training set is 5K. 5K, yes, that is. Supercut is 10K. Probably most people here know what the right answer is. But okay, the main point I wanted to make here was that this duplicated images that we found, or near duplicates, are not close to any images in the training set. So again, in line with the theory. It's not that the generator learns to reproduce images in the training set, but it produces new images, but not a lot. Alright, so recap of the talk. Theory suggests that GANs training can appear to succeed any other learned distributions for distribution, and tinkering with objective doesn't help. And they also exposed 3 articles about this on my blog. All of empirical studies suggested that this problem does arise in real-life training. And again, we haven't checked it for the latest and greatest GANs. Can real-life GANs training be modified to avoid such issues? And some of the analysis must take into account some properties of the optimization part of the real-life distribution. And there's a recent paper by some of my co-authors which takes the first step in accounting for the distribution. Where to go from here? Well, it could be that there are GANs variants out there. There are, at this point, dozens of GANs variants, and we haven't tested all of them. Maybe some of them already are better at evading mode collapse than before. Than we know so far. Maybe that we can formalize other ways in which GANs are useful, for instance, as image-to-image mappings. Again, there's not much theory here. Finally, I think this whole equating representation learning, which was maybe one of the goals of GANs, with distribution learning is maybe not the right way to do representation learning. So I have an expository article on my blog arguing this point. And so, yeah, we need a more complete theory of GANs, which incorporates finite size deep nets and all the other issues. And also, and probably we'll need to understand the dynamics of training, which is a very, very big theoretical open problem for deep learning in general, that we don't understand the dynamics of non-context optimization. Thank you very much, and I'm happy to take questions.
So in the analysis you mentioned use the number of parameters in the network for the analysis. Just wondering if the other ways you can analyze these networks, not only in terms of the number of parameters of the networks, maybe some other. We've seen some other ways to.
Yeah. So notice that. The general feeling is that the number of parameters is a crude upper bound on the capacity map, that the true capacity is a lot lower. So if the capacity is lower than the number of parameters, or whatever is implied by the number of parameters, our results can incorporate that as well. So this is still a crude upper bound on the support side of the distribution. So the news is in the correct direction. Right? The bad needs to be upper bounding, right, the support side. So that won't help. Yeah, you'll only get a better estimate.
Yeah, I like your epsilon net argument for looking at the networks from a very coarse scale, let's say. I was wondering for your last experiment where you were making grad students look at duplicates, whether you could pull a similar argument like looking at cosine similarity of the images or looking at a histogram of cosine similarities to spot these images up more easily and in a more structured fashion.
Yeah, so we're using those automated filters already.
Okay.
To narrow down from a sample of size 1,000 to like the 25 most plausible collisions.
You have to look at it.
Yeah. So notice that again, as in the answer to the previous question, is an error in the correct direction, right? So our estimates so when we find a collision, it's verified by a human. So that's presumably a real collision. So using your filter, we may find more collisions, not less.
Yeah, exactly. Okay.
Yeah. So it's an error in the correct direction. It won't save the theory. Yeah.
Can you just go back to the DC GAN slides in which, So in this, if you see that the fourth image, the woman does not smile that much, and on the left side she does smile. So we want to be able to learn these manipulations as well, right?
Yeah.
Transition. So this might not be two very similar images. This might the last on the fourth quadrant.
Actually.
So she's smiling.
There's no truth. She's smiling, but yeah, it's not true.
But it's different kinds of smiles, right? So we need to learn these as well, to smoothen out the manifold. So wouldn't that be also a desirable characteristic to learn the different kinds of smooth transitions between the?
Yeah, I agree. But I think it's still rather close, right? I mean, given that celeb A has all kinds of variations, right, for the same celebrity. So this is rather close, I would say, for celeb A. So, I mean, it's fine.
So in all of them, there are subtle differences. For example, even in the one on the left, you see the jaws being slightly more wide. So these manipulations are especially valid for graphics people. For example, in Adobe or these companies, it might be desirable to learn these different kinds of variations, right?
I agree. So I guess my only point is that we can all agree that they are like doppelgangers, right? Like, and we rarely know any doppelgangers in real life except twins, identical twins.
But
you think those two people look alike, but then they're standing next to each other.
That is true, but my point, the question I'm trying to ask is that these duplicates are not exact duplicates in terms of some metric you want, and maybe in terms of some metrics it might be near duplicates.
Yeah, totally bad.
So I don't have time for the questions. Maybe we can discuss offline.
Yeah.
Yes.
Exactly.
Sorry about that. So next speaker is Abby Jensen from NYU. She is a student working with Rob Ferguson. I think her work really motivates my work. And I think I remember in 2015, I showed the GAN papers at Berkeley Vision Group, and everyone thinks it's a beautiful idea, but it's not working. And I started working on GANs in 2015, and I can't make it work. I almost give up. And Abby Jensen came up with beautiful paper on Laplacian GANs, which produce much better samples compared to other generative models. And you can see the future from her paper. So here she is.
Awesome, thanks for the introduction. Okay, yeah, so I'm Emily from NYU. So today I'm actually not going to be talking about generating images with GANs. Instead I'm going to be talking about using adversarial losses in feature space to shape and impose some kind of constraints on learned representations. So just a super brief summary. Standard GAN setup here is we have some Z sampled from some prior noise distribution. This goes through a generator network, produces an image which is passed to the discriminator, and then the discriminator is determining whether or not it came from the real or generated distributions. So in contrast, I'm going to be looking at this different sort of setup. So the idea here is we have some input. In most cases that I talk about, it'll be an image, but some input. It's going to go through some encoding, and we're going to get some kind of feature space. And then there'll be some tasks, some downstream tasks that we care about, such as classification or reconstructing the input. And then we'll have some discriminator that's attached to this feature space as well. And we'll have some adversarial loss that's there to impose some kind of constraint on this learned representation. So this talk is going to be broken up into two parts. First, I'll talk about some work that I've done using adversarial losses to disentangle content and pose in video sequences. And then I'll do a brief sort of survey of related adversarial losses in different types of problems. Okay, so the particular model that I worked on is called a disentangled representation net, or DRNet. The idea here was that we wanted to factorize image sequences into temporally constant and temporally varying components. So what's constant and what's varying across time in a video sequence is going to change from video to video. In this particular example here, we have the lighting, the background, the person's identity. All those things are constant across time, and what changes is the person's pose as they walk across the screen. So the idea is we want to have two encoders, a content encoder and a pose encoder. And the content encoder is going to extract information that's constant across time, and the pose encoder is going to extract information that's changing across time. So the way in which we learn this disentangled content pose representation is by training with a combination of three different loss functions. There's a reconstruction loss, a similarity loss, and an adversarial loss. The adversarial loss is kind of the most interesting thing to this crowd, but I'll go through the other ones so you can see the full picture. So the reconstruction loss works as follows. So we have this content encoder and a pose encoder. These are just two separate convolutional neural networks, different weights. And the content encoder and the pose encoder are each going to see a different frame from a video sequence. And they're going to encode that frame into a content vector and a pose vector. Then we have a frame decoder that takes the concatenated vector of the content and pose vectors, and it's going to try and reconstruct the frame. The frame that it's trained to reconstruct is the frame that was given to the pose encoder. So if you look at this diagram here, you see that if we just look at the pose encoder, frame decoder pathway, all we have is a standard autoencoder. So how do we actually make it so that the pose encoder does something more than just represent the entire image? And in fact, what we want to do is have the content encoder contain everything about this future frame that's predictable from the past. And then we only want the pose encoder to represent things that are changing across time. So in other words, anything that that is constant across time, we can predict from the input that's being given to the content encoder. And then anything that's not constant across time, anything else in this particular instance, the pose of the body, that's the only thing that we want to pass through the pose encoder network. So that's the basic idea. So first we have a similarity loss, and this is going to make sure that content vectors are invariant across time. So this is really simple. We just extract two content vectors from different frames in a particular sequence, and we just ask those to be similar. We use a mean squared error loss here. This is very similar to like slow feature analysis and previous things that existed. We just want similar content representations for nearby frames in a video sequence. Then the adversarial loss, this is where it gets interesting. So this is what we use to make sure the pose encoder only contains information that's changing across time. So another way of phrasing this is that we don't want to be able to distinguish from a particular pose vector which clip that came from. So the way we do this is with an adversarial loss. So the idea here is we construct what we call a scene discriminator. So this is analogous to the discriminator in the standard GAN setup. And instead of in the standard GAN setup where we have some fixed data distribution and then some synthetic generating distribution, instead we're going to construct two different distributions from the pose encoder network. So one of these distributions is going to be pose vectors that are extracted from the same video sequence. So we're going to extract two pose vectors from two frames in the same video clip. The distance between those two frames can vary, but they'll be sort of temporally close to one another in the same video clip. And we're going to pass the concatenated set of that pose vectors, and we're going to pass them into the scene discriminator, and that gets a target one of being from the same scene. And then the other distribution is going to be taking two frames from two different video sequences. Just again, randomly sample two different video sequences, sample a frame from each, pass those frames to the pose encoder, we concatenate those representations and pass them into the scene discriminator. And in this case, the scene discriminator is going to get a target of 0. So the scene discriminator is trying to determine, did this pair of pose vectors come from the same video sequence or a different video sequence? So that's the way the scene discriminator is trained. And again, analogous to the standard GAN setup, when we're training the scene discriminator, the pose encoder is held fixed. So when we train the pose encoder, now the scene discriminator is held fixed, and it's just used to construct the loss function. So what we want to do here is maximize the scene discriminator's uncertainty about the content of the video. So what that means, since we have a binary output, 0 or 1, we simply give a target of a half, and this is analogous to asking the scene discriminator to output a uniform distribution. In other words, be maximally confused about the content of the video. Okay, so when we put this all together, we have this content encoder, this pose encoder, and a frame decoder. And again, we're training with this combined loss of a reconstruction loss, a similarity loss, and an adversarial loss. Okay, so why is this interesting? So a couple things we can do with this. So the first sort of simple toy experiment we did was we constructed a sequence of frames. We created our own video sequences by taking just 3D models of chairs and just rotating them about their center axis. So in this case, in a video sequence, the thing that's constant across time is the chair's identity, and what's changing is the orientation. So if we train this encoder-decoder model of this type of data, then we're able to do some nice things like image synthesis by analogy. So for example, we can take a content image, so some chair, and then a pose image, another chair, and then synthesize a new image. And this synthesized image here has taken the content of the chair from the content image and rotated it to be aligned with the chair given in our pose image. So this just shows a whole bunch of examples there. So here, the top row shows the images given to the pose encoder, and then the green column here shows images given to the content encoder. So the way you read this is, for example, this second line here, we're taking this chair and we're rotating it to be aligned with the pose of this chair at the top. So the interesting thing here is that the network was never trained to do this particular task. We didn't have this kind of aligning of images during training time. All we did was have this kind of grouped data where we have sequences of videos where something is constant and something is changing, and we're able to do these nice kind of analogy tasks. So another nice thing we can do is interpolation in pose space. So here what we've done is we take an image and we encode the content vector from this x1 column, and then the content vector remains fixed. And then we encode a pose vector from x1 and a pose vector from x2, and then we just do linear interpolation in that pose space with the content vector held fixed. context. And so you can see that we nicely are able to kind of rotate chairs from one pose to another just by doing this simple interpolation in pose space. Okay, so a slightly more interesting task is video prediction. So video prediction is a very challenging problem. One of the challenges here is that you're kind of combining the problem of predicting the future with the problem of sort of representing and generating images. So one broad approach to this is to first learn an image representation that then affords a kind of prediction in that latent space. And so that's exactly what we've done here. By factorizing images into a temporally constant and a temporally varying component, we're able to do really simple video prediction by just training a predictive model to predict the component that's changing across time. So what this looks like is we've trained our content encoder and our pose encoder offline. So we trained that with that sort of disentangled representation framework. Now we have those fixed, and we take a video sequence. So we're going to take our pose encoder, and we're going to encode a whole sequence of video frames. And then we're going to train an LSTM to take in some sequence of these pose vectors and predict future sequences of pose vectors. So the nice thing, again, is that we don't need to worry about the content vectors when we're training this LSTM, because by design, the content vectors are going to be fixed across time. So at test time, we can now generate a video sequence in pixel space by just encoding the content vector from one of the past frames that we had access to, and then feeding the predicted pose vectors and the content vectors into our decoder, which again was trained in that previous process and is now fixed. And now we're able to decode back to pixel space. So we've kind of reduced the problem of generating video frames into first learning to represent and generate images with a nice kind of learned latent space that affords this downstream task of video prediction. And so another nice thing about this is that we're never actually recursively feeding back in images into our model. So typically when you train sort of predictive models with LSTMs, at test time you're going to be feeding back in your generated output back into the model. And if you're doing this with images, then small errors in the predicted image will get fed back into the model, and these will amplify over time. They'll just get fed back. But in our case, we're never actually feeding back images into the model. And so we might have small errors in the predicted pose vectors, but these aren't going to really amplify in pixel space. So this shows an example of training this on a moving MNIST data set. So this is just two MNIST digits colored green and red, and the digits are just bouncing around the screen. So what's nice here is that I'm actually going to run out this generation up to like 500 time steps, and since the content vector remains fixed, the digit identity remains very consistent and constant across time. And the pose vector is only encoding the location of the two digits, and so we're able to, this model was trained, I think, to take in like 5 video frames, or 5 pose vectors, I should say, and predict the next like 5 or 10 pose vectors. But we can just kind of like keep running this on forever, since this prediction is in latent pose space instead of image space. Okay, so the KTH dataset is another dataset of more real-world videos that we trained the model on. It's still very toy. It's very simple, but it's a little bit more complex than the kind of moving MNIST setup. So the backgrounds are pretty uniform, and they change from video to video, but are fixed within a video. And we have just videos of people performing different actions, like walking, or clapping their hands, or waving their arms. So we're going to compare against a baseline, which I won't go into too much detail about, but it also tries to separate out motion and content, so not exactly the same thing as what we're disentangling, but a similar sort of style of separating out kind of stuff that's changing from stuff that's constant. But they do their prediction in pixel space, and so as we'll see in some examples, small errors in pixel space end up getting amplified. So, okay, so this is an example of generations. So here we had 10 conditioning frames. So the model was trained to take in 10 vectors and then predict 10 vectors. And here we're actually going to run it into 30 time steps, so we'll see a little bit of the generalization capability of the model also. The top row is the ground truth, the next row is our model, the next row is if you train an LSTM on representation learned by an autoencoder. So this is very similar in that we're doing the prediction in latent space, but we don't have the adversarial loss, we don't have anything that's enforcing this disentangling of content and pose. And so this baseline here is really kind of getting at, how much do we gain from just doing prediction in latent space versus doing prediction in a really kind of nicely shaped latent space learned by this disentangling model. And then the bottom here, we see this motion content net. So the motion content net is actually quite good, but you see if we do really long-term prediction, then it starts to devolve. So there's some examples here. So here we're actually running out to 100 time steps. And again, the model was trained to predict 10 time steps in the future. Same thing with the MCNet. And so running out to 100 time steps is really like pushing it past what it was trained on and just looking at the generalization capabilities. So we'll see that the DRNet tends to kind of stick to the image manifold, and even 100 time steps into the future is kind of producing plausible actions, whereas this MCNet, early on it produces good actions, but then small, tiny errors in pixel space will get fed back into the model and propagate. And here's just a couple more examples of this. So one thing I should say is that our model isn't necessarily sort of better or worse, it just has different types of errors. So here, if you look at, I guess, your right screen, we'll see we had a person just walking across the screen, and now you'll see him just kind of walking backwards across the screen. So this is an example where, like, we're kind of sticking to the image manifold, but, like, this is weird, this shouldn't be happening. So just because we don't see the same kind of, explosion of, like, weird pixels that the MCNet does, doesn't mean that our model is, like, perfect. It just kind of fails in different ways. So just something to keep in mind. Okay, so another cool thing we can do with this is look at nearest neighbors in pose space. So again, this is really kind of getting at how well this adversarial loss was able to disentangle content in pose. So the top row here shows generated images from our model. And then the second row shows nearest neighbors in the training set of the generated images when we look in pose space. So the cool thing here is that when we only look in pose space, we see that sort of corresponding top and second rows, the people are in very similar poses, but the content of the image is totally different. So this shows that the adversarial loss has actually done a really, really good job of separating this temporally constant and temporally varying information. And then the bottom row here shows nearest neighbors in pose and content space. And then here we see a little bit more of, the body position being similar, but we also intend to retrieve images where, like, the background is the same and the person's clothing is the same. So this is another reason of doing this is just to make sure we're not, like, memorizing the training set. So this is sort of a test for how well we've disentangled things, and also a test that we're not just, retrieving stuff that we saw in training time. And then here's just a couple more examples of that. Again, I think the most interesting one to look at is the comparison of the top and second row, where we see that the pose really matches, and the content does not at all, which is what we want. Okay, so this adversarial disentangling technique is super general. It could be applied to any other data set where some kind of weak labeling is available. So again, all we needed was sequences of images where something is constant and something is changing. And we used video because then you get this kind of weak labeling for free. Because if you take video sequences, then likely within a sort of temporally local neighborhood, you're going to have something being constant and something changing. Again, what is constant and what changes will differ from video to video, but you tend to have that property. But when we were training the disentangled representation part, we actually don't need video sequences. All we need is that group of data. So, for example, you could take a data set of human faces with, like, a bunch of different people with different hairstyles and, with glasses or no glasses and whatnot. And as long as you had some kind of labeling of, like, what images consisted of the same person, you could apply this technique to separate out, say, a person's identity from, the particular way that they dress themselves up that day. So this is a very sort of general approach. Okay, so the last 10 minutes of the talk, I'm going to go into kind of a survey of very similar uses of adversarial losses for different problems. And again, just to kind of, like, unify this into one little diagram, we typically have this kind of encoder network and then some further layers that are going to be used for classifying or reconstructing an image or something like that, and then we're going to have our adversarial objective. So mapping this onto what I just showed, we had this encoder network, which was like this pose encoder. We had some kind of reconstruction loss where we were trying to reconstruct the image. and then our discriminator was that pose discriminator, where we were trying to classify whether or not images came from the same or different scenes. So the first example of where this is used is domain adaptation. So I'll give a super brief summary of this. I think there's going to be a speaker in the afternoon who's going to go into a lot more depth of different ways of doing this, but I just want to kind of give a high-level summary of how this is related to what I was doing. So the problem with domain adaptation is you have some labeled examples from a source domain, and then you have a target domain where you either have no or very few labels. And the idea is you want to be able to train a classifier on the source domain, and then actually be able to transfer what you've learned on the source domain to be able to make predictions in the target domain. So where an adversarial loss can be used here is to learn some kind of domain invariant features. And this will allow that source classifier to be used on the target domain. So this is the kind of general setup of adversarial domain adaptation. There's lots of sort of different tweaks that different algorithms might use. For example, the source encoder and the target encoder could share weights or have different weights. Maybe you have some part of the sort of feature space that is shared and then some other part that's not shared. And then another thing that can change is the actual adversarial loss that you use for the domain discriminator. So there's a couple of different ones that have been proposed. Gradient reversal loss is the first one that I know of that was proposed. And this is just the standard GAN setup. Then the label flipping one is the GAN setup that people use in practice, where the generator tries to get the discriminator to output a label of 1. And then uniform target loss has also been proposed, and this is the same loss that I showed in the DRNet, where the target encoder is trying to get the adversary to be maximally confused about what domain the image came from. Okay. So another use of this is learning fair representations. So this is a really closely related problem to the problem of domain transfer. So the idea here is instead of having some source domain and some target domain that you want to learn some shared feature space of, you have some data and you're trying to make some prediction about that data, but you have different demographic groups, different subpopulations, and you want the representation to be fair with respect to these different subpopulations. And there's many different notions of fairness, way too many to go into here, but the basic idea with adversarial learning of fair representations is to have some kind of discriminator network that's predicting a sensitive attribute. So the idea here is that one way of not using a sensitive attribute, for example, gender or something like that, is just to not include it in the input. But oftentimes that sensitive attribute is going to really correlate with other aspects of the input. For example, zip code of where somebody lives is going to really strongly correlate with race. And so even if you don't include race in the input, you're still possibly going to end up with a really biased classifier because you can use this other information that's highly correlated. So by using an adversarial loss, you can make sure that these representations are not actually encoding anything at all about the different subpopulations that you want to be fair with respect to. And so there have been many different formulations of adversarial objectives, and each one kind of achieves a different notion of group fairness, such as demographic parity or equality of opportunity. So for example, making sure that for different subpopulations you have equal accuracy rates or equal false positive rates or something like that. Okay, so one other use of this is learning independent components. So I think this is a really nice idea. So the idea here is that if you're training, say, a variational autoencoder or some kind of encoder-decoder model, you might want the components of your code to be independent. So this is work that was presented originally at a NITS tutorial, and I think is going to be presented in sort of a fuller-length version of this ICML. And the idea here is to have a discriminator, and the two different distributions that you're going to give the discriminator are either the marginal distribution of your code or the product of the marginals. And the way you get the product of the marginals is just by kind of permuting the different elements of the match. So it's a really nice, simple, easy way of doing this. And the discriminator either sees the marginal distribution of the codes or the product of the marginals and is trained to discriminate these two. And then, of course, the encoder is trained similarly to make it so the discriminator cannot solve that. And then this is also super related to earlier work on predictability minimization by Schmidt-Huber. And this is the kind of case where codes are discrete The idea there is to make sure that given all the remaining codes except for one, so all the remaining units except for one, you don't want to be able to predict that remaining one. So it's the kind of discrete setup here. And then, finally, this is kind of getting a little bit further away from the like having an encoder and an adversarial loss, and a little bit more into like the generative model space. And again, I think an afternoon talk is going to go a lot more into this, but just a couple other uses of adversarial losses in feature spaces are to match prior distributions of generative models. So adversarial autoencoders were proposed a couple of years ago, and the idea here is to have an encoder, decoder. Again, it could be trained with a mean squared error loss, and instead of matching the approximate posterior with for example, like a closed form KL loss, you could use a GAN to match the aggregate approximate posterior. Or, more recently, adversarial variational phase has been proposed, which actually ends up minimizing the same thing as a VAE, but instead of using this closed form KL distribution, you're able to use this adversarial distribution. So one nice thing about these models is that you can pick a prior distribution that is essentially arbitrary. You just need to be able to sample from it, as opposed to if you're going to use a KL divergence loss, then you need to sort of restrict the space so that you can have some kind of nice closed form solution, or at least something that you can actually optimize. So these are, in some sense, more general, because you can use any prior distribution as long as you can sample from it. And then the final thing that I'll mention is adversarial feature learning. And again, this is kind of like moving more and more back into the standard GAN setting. And the idea here is to have a GAN loss that works on images and latent codes. And so this is kind of tying in the standard GAN setup with a representation learning setup and learning an encoder and a decoder jointly. So yeah, that's my brief kind of summary of different kinds of uses of adversarial losses in feature space. Of course, I just kind of like touched on a whole bunch of different things, hopefully to give you guys a big survey. And if you're interested in any of them, this is a whole set of references of people who worked on this. Pointers for where to go. And yeah, thanks.
Thanks for the great talk and great nice work on this tackling content and pose. I saw that your results were on the data set that you had variations of the pose of the same object in different angles, right? In many cases, we don't have that. We have the variation of that object class in different angles, for example, or different variation of this object class, not the object instance. Have you tried anything on that domain?
So I haven't tried applying this to anything other than very sort of simple data sets like this, particularly with video generation. But, so one thing that I didn't talk about here, which I think is what you're maybe getting at, but let me know if I'm not answering your question, is, so one thing that's nice about this is that the content and pose, so I'm using content and pose, but those are very loose terms. It's really just stuff that's constant versus stuff that changes. So for example, if you just took like a data set of, I don't know, like any images where you have some kind of class labels, and you apply this just to images with that. So basically, your group's data would just be totally different objects or totally different images of the same class, and then train this model. That I think you would still end up with some kind of separation. So, go ahead.
So what if you had chairs, but different type of chairs, but variation of, but you know the variation of the pose.
Right.
So still chairs, but not the same chair. It's a class of chairs, but you know exactly what the angles.
So you know the poses. Okay, so there's, I think that if you know the individual poses of the chairs, then this might not be the best method. You could use it, but if you have that information about the poses, then why not use it? And in some sense, this is like an unsupervised approach. If you don't know the pose information, but you just know that like these things are similar in some way, then it's useful. You can still use it if you know the poses. I just think that like if you have extra information, then you should try and use it if you have it.
You have the poses, but let's say for one of the chair types, you have it in 60 degrees. You don't have it for other angles. the other picture you have it for 30 degrees, not the other. Because you have the variation, object class, but not the instance.
I see. Oh, I haven't. Okay, so you're asking, I think, if some of your instances have more some of your sequences or group data have more variation than other ones, then would the variation transfer to the other one? Is that kind of the question?
That can be an example.
Gotcha. Okay. So I haven't tried that. I mean, I think it would come down to how much of your data did cover the full space. I imagine it would do a pretty good job actually of filling the space. So for example, one thing that kind of lends into that is the DRNet images. What you can do is take the content and pose of two different video sequences where one video sequence is a person who's clapping their hands and the other one is a person walking. So that's an example where the actual poses in those two video sequences are super different, but you can still kind of map one onto the other. So I imagine that if for some of the data you had kind of enough of the space covered, it would be able to kind of fill it in for the rest, but I haven't tried it.
Thank you.
Just one more question.
Yeah, hi. That was pretty amazing. So I guess it ties into a little bit of what he was asking. So I was just thinking about how you would predict someone's dance moves. There's a video of someone dancing, especially different forms of dance. So I guess it ties into the fact that you said that if it covers enough of the space, you could try it out. But
yeah, I think that'd be a really cool application. I mean, I think it's really interesting for human pose where you don't. It's very expensive to get full annotations of a human pose. So here it's just as long as you have video sequences of people looking the same but doing different stuff, then you can kind of automatically extract the pose of the person.
Yeah, and also what happens if in sound frame you have a little bit of noise? What kind of pre-processing would you do to eliminate non-uniformity in the background and stuff
Right. I mean, the thing is that I think it kind of depends on how so. If you do have camera motion or something like that.
So suppose in that in the video where the guy is walking, and you have, say, a couple of frames where a bird is flying by in the sky. So what do you do with that?
Right.
Does the bird fly back?
Right. Yeah. So in that case, so if you just apply this model directly, then any of that kind of bird flying through or stuff like that, that would all get encoded into the pose vector. Okay. And then maybe you would end up in some sequences a bird just randomly flying
around.
Yeah. But I mean, you could use some kind of I don't know, very simple tracking of objects not in the center or something like that to get rid of that. But I think if you just use this method, and there were enough instances of birds flying through, then the pose encoder would probably learn to just sometimes throw a bird in there.
Okay, thank you. That was good stuff.
Let's thank our speaker again. Afternoon session will start at 1:30, and we will talk about VAE GANs and detection segmentation in robotics. So have a great break and see you later. Thanks.